So here's a question that we get a lot. Do harmonics naturally cancel on the power system? Meaning, do I get some harmonics from one load to cancel with some harmonics from another load? So to answer that question about whether harmonics cancel naturally or not, I usually use the example of these 4 drives up here. So if we take the drives, if you put one drive on, it draws about 12 amps of fifth harmonic current. So you would think all 4 drives would be roughly 48 amps, and it turns out to be about 42 amps. But there's a reason that the harmonics reduce, and it's not because they're canceling with each other. I'll show you an example of why that works on paper. So if we look at our power system and we have a transformer here, and let's say we have 4 drives. 1, 2, 3, 4. So we have 4 drives, and they all produce a spectrum of harmonics that we would expect for 6-pulse drives. So we have fundamental, we have 5th, we have 7th, 11th, and 13th, for example. If this one drive by itself produced 12 amps of 5th harmonic current, then we would expect that all 4 of the drives, if they're the same exact drive, would produce the same amount of harmonic current, and that would be the case if we did one drive by itself. So we'd say 12, 12, 12, 12. But in fact, if we turn all 4 drives on, it's really more like maybe 10 amps, 10 amps, 10 amps, and 10 amps. So why the difference? Why is it different when we put 4 drives on versus having just one drive by itself? And the reason is because of this guy, the transformer. This transformer ends up looking like a line reactor. And what does a line reactor do? We've talked about it many times, but it basically constricts the current. So if I have a steep current that looks like this, when I put a line reactor on, I essentially get something that looks like this. It spreads it out a little bit, and it reduces the overall steepness of that. So that line reactor, being the transformer, reduces my overall harmonic current. So instead of being here 48 amps, it's more like 40 amps. And again, this is something that you probably wouldn't think about if you just thought about one drive by itself and you modeled this in a program, and the model is going to take 12 for every one of these, but in reality it's going to be less. Now, why is that the case? Let's say that transformer is 300 kVA, okay? And let's say that each drive is 30 kVA. So to get the actual impedance, we would take 30 kVA or 30 horsepower divided by 300 kVA for the transformer times the impedance of the transformer. Let's say it's 5%. That turns out to be 0.5%. And so the effective impedance of that transformer at a very light load with one transformer is 0.5%. But as you see, as you add more and more drives to here, this number becomes bigger. And as a percentage of the total impedance, this number becomes bigger. So then this looks more and more like a line reactor. And so really that's the case. And so as the current flows up through the transformer, this constricts the flow, and we reduce the harmonic current from something that looks steep to something that looks a little more smoothed out, like we've talked about many times with line reactors. The other example of what could happen is where, and we've talked about this in other videos also, I've got a delta delta or a delta zigzag and a delta Y. And my 5th harmonic over here, you know, again, 5 times faster than 60 hertz, and my fifth harmonic over here, 5 times faster than 60 hertz. When they add up top here, they're actually equal and opposite of each other. So the 5th, and in fact the 7th harmonic, cancel each other out at this point. So I'm left with the delta Y delta delta, I'm left with not a 6-pulse drive. My 5th and 7th go away. I'm left with 11th and 13th, or really like a 12-pulse system. So to answer the question again, do harmonics cancel naturally? No, they don't. What happens is power systems reduce the amount of harmonic current that's allowed to flow as you add more and more harmonic load. That's the natural form of impedance that's affecting you. but they can cancel when you use purposefully phase shifting transformer or impose some sort of phase shifting on the power system.